Good afternoon, I think. Yeah, good afternoon. Hopefully everybody went and picked up one of the handouts. If you didn't, you probably want it, because today is application problems, which means word problems. And so I made a handout. I believe I shared this on the My Math Lab site, so there's one up there as well that you can print off if you need another one, or if obviously you're not here and you're watching the video. So on Monday, we did 3.1 and 3.3, where we talked about the unit circle, and we talked about converting into radians and all that kind of stuff. And today, what we're really going to talk about is arc length. That is the one topic that we are discussing. And then we are applying that to these different word problems and situations. So they're literally that first little section up here. This is the only bit of notes for this section, and the rest are just how to approach these different problems. So arc length is the length S of an arc intercepted on a circle by radius r with a central angle with the measure of theta radians is given by the product of the radius and the radian measure of the angle. That's a lot of stuff to say that the arc length, which is represented by S, equals the radius times the angle, where the angle is in radians. That's all we're doing. So it makes it sound a whole lot more complicated than what it actually is. Most of these are pretty easy algebraically once you get them set up. So to find the arc length, which I think down here with this second problem, it's actually, you can kind of see what the arc length is. It's this outer portion of the circle. Like if we walked around it, it's pretty much like the perimeter of a circle. We talked about that a little bit in 3.1, 3.3. So for this first example, it says a circle has a radius of 18.20 centimeters. We need to find the length of the arc intercepted by a central angle having each of the following measures. So the first one is given to us in radians, which is good. That's what we want it to be in. Because up there in the definition, it specifies that we need theta to be given in radians. So if it wasn't in radians, we would need to get there first. But lucky for us, it's already in radians. So it's really as simple. Arc length equals the radius times theta, as long as theta is in radians. Well, the radius, they told us, is 18.20 centimeters. And the theta is 3 pi over 8. Because these are word problems and because it gave you a decimal to get started with, you're going to be giving a decimal back out. Even though it doesn't specify, let's round it to 2 decimal places. So if you typed that bad boy in, you'd get approximately 21.44 centimeters is the measure of the arc length when the radius is 18.2 and you have a theta of 3 pi over 8. So not too bad. Pretty much a plug and chug style problem. For part B, you do have to do a little bit more because it gives you the angle in terms of degrees instead of radians. And so we need to convert that into radians. From Monday, or from 3.1 and 3.3, we learned that to convert from degrees to radians, you multiply by pi over 180 degrees, and that's going to give you your radian measure. I would always leave it in terms of pi because that is going to be the most accurate answer. If you were to go ahead and convert that to a decimal, you're going to have to do some form of rounding, and then when you apply the radius to that, then you're going to be rounding some more. And so it's best if you can leave it as pi's for as long as possible. So again, though, we're doing the same process. The arc length is the radius times theta, now that we have theta in radians. So we're going to take 18.20 times 4 pi over 5, which is approximately 45.74 centimeters. Are there any questions at all about how we did these first two? All right. Then let's do some latitude. This problem is one of the reasons why I made a handout, because I didn't want you guys to have to write all that stuff down. It says latitude gives the measure of a central angle with the vertex at the Earth's center, whose initial side goes through the equator and whose terminal side goes through a given location. So Reno, Nevada is approximately due north of Los Angeles. The latitude of Reno is 40 degrees north, and that of Los Angeles is 34 degrees north. The north in the 34 degrees north means north of the equator. The radius of the Earth is 6,400 kilometers. Let's find the north-south distance between these two cities. So we're not finding the actual distance between Reno and Los Angeles. What we're finding is how much further north is Reno than Los Angeles if they were on the same plane, not going diagonally. So they give you this really nice picture showing you that the equator is 6,400 kilometers. To Los Angeles, we have 34 degrees, and to Reno, we have 40, which means going between Los Angeles and Reno, we have a 6-degree theta. And that's actually what we are concentrating on, is this 6 degrees, because we want to know what is this arc length right here between Reno and Los Angeles. Well, if we know it's 6 degrees, we can convert that over to radians, to where it's pi over 30 radians. Now you do the same thing we did on the previous two problems. The arc length equals the radius times theta. The radius in this case is the radius of the Earth, which is 6,400 kilometers, times the pi over 30. If you type that in, you get approximately 670 kilometers. The examples that the textbook gives, it's never very specific on how many decimal places it wants you to round. But the examples that they give in the My Math Lab program are very specific in the blue or the green words next to the answer boxes on how much to round or not round. So you won't be left questioning there. Switch over to this one so you don't see the previous writing through it as much. Example 3, finding the length using the same equation. So it says a rope is being wound around a drum with a radius of 0.8725 feet. And they give you a nice picture yet again. So how much rope will be wound around the drum if the drum is rotated through the angle of 39.72 degrees? We're literally not doing anything different, except that we will have to convert our degrees over into radians. And since the degrees are already given as decimals, what I recommend doing is leaving it all as one big, long expression. So the radius in this case is the 0.8725. And then the theta needs to be in radians, but right now it's not. So I would write down your degree, which is 39.72, and then to convert from degrees to radians, you would multiply by pi over 180. And I would leave it all as one big long expression instead of doing it by parts. Again, because if you type all this into your calculator is only going to round or do the estimation one time instead of rounding multiple times and thus getting further and further away from the true answer. You can do it the other way, but you have to be really careful about how you're rounding and understand that you could be off a little bit. And while you're off just a little bit, if it's only having you round to 1 decimal place or 2 decimal places, that could make the difference in the outcome of your number. So just be a little bit careful on that. This one, according to the book, they had us go out 4 decimal places because this started off with 4 decimal places. So it was 0.6049 feet. So a little bit over half a foot of the rope will get wound around that drum. Any questions so far? Super exciting, yeah? Gotta love word problems. at least they're all very similar in that you're using the same formula every single time. You're really doing the same process every time. This next one does get slightly more complicated because we are talking about two different gears at one point. And so we've got two different radii going on and things like that. And it says two gears are adjusted so that the smaller gear is driving the larger one, as shown in the picture. If the smaller gear rotates through 225 degrees, through how many degrees will the larger one rotate through? So the first thing that you need to figure out is you need to find the arc length of the smaller, gear. Because once we know how much that one turns, we can determine how far the second one is actually turning as well off of that. So again, I'm going to use one long expression like I did in the previous problem, because I'm going to think about the arc length of the smaller one as the radius of the smaller gear times the theta. The radius of the smaller gear is shown as 2.5 centimeters. You don't have to write the centimeters, but I did. And then it says the smaller gear travels through the 225 degrees. So 225 degrees, but we need to convert that to radians. So I'm going to take 2.5, and in this case, because we're not going to be done at this point, if you can keep it in terms of pi, it's going to be beneficial to you. So how do we keep it in terms of pi? Well, we would have 2.5, and 225 divided by 180, it does work out semi-nice in that we get 5 pi over 4. And if we multiply 2.5 by 5, we get 12.5 pi over 4. Now, we never like decimals inside of fractions because that's just doubly gross. So if we double both the top and the bottom, though, we will get rid of that decimal to where we have 25 pi over 8. Could you do all of this with decimals? Yes, but again, you're risking rounding issues at the very end. So the longer you can keep it in terms of pi, the better. And on the previous problems, we would have already been done because we only found the arc length of one thing on all the other problems. But this time, we're finding the arc length of the smaller gear so that we can figure out how far around the larger gear actually travels. So if we're looking at the larger gear, if we know the arc length of the larger gear, because it's the same as the arc length of the smaller gear, and we know the radius, then what we're missing is we're missing the theta, which is how many degrees we're rotating through. So we have different pieces of the puzzle instead of just having the r and the theta. So for the larger one, we just found the arc length. The arc length is going to be the same because it was so far on the smaller one, which will be the same distance on the larger one, which is 25 pi over 8. The radius, though, for our larger gear is 4.8, and it's the theta that we're missing. Now, you could do this a whole bunch of different ways. You could type it all into your calculator, do 25 pi divided by 8, and divide that by 4.8, and you're going to get something that is in terms of radians, but it wants to know how many degrees. So we're going to have to convert it over into degrees. So I'm going to show you out on paper, like pretending that we don't have the use of a calculator till the very end of this problem. Because I think seeing the process of how to do this without a calculator is very helpful. So at this step right here, I have a fraction set equal to a decimal. I don't like that, so I'm going to convert my decimal into a fraction. And then I'm going to take it one step further and simplify that down to 24/5. That way I have 25 pi over 8 equals 24/5 theta. To solve for theta, I would multiply both sides by 5/24. Because that'll cancel. Sorry, that went off the screen a little bit. When I do that, I find that theta is 125 pi over 192. So if I was leaving it in radian form, I'd be good to go, but it wants to know how many degrees. When you go from radians to degrees, you take 180 divided by pi. Notice I've kept it with pi as long as possible, again, so that I don't have to worry about the rounding. Now at this point, I would do the rounding because the pi's would cancel, and it shows me that I'm traveling approximately 117 degrees around the larger gear. I know some of you are going to be very tempted to use your calculator, and there's nothing wrong with that. Just know that you're going to have to be really careful about how your calculator is doing the rounding. And if you do use your calculator, if you're writing anything out on your paper, you're going to want to include as many decimal places as possible for as long as possible, so that when it comes to the final answer, you're getting 117 instead of 118 or 116 or 115 because of rounding. This one is pretty much as complicated as it gets because you have to find the arc length once, and then you have to use the arc length in order to figure out the theta on the second gear. Are there any questions about any of the steps that we took on this one? Okay. There is one more topic. And we do one problem from this topic, and it's the area of a sector of a circle. And the area of a sector of a circle looks like a fancy A. Somebody in this class already has a really fancy A. That's all on the test. So this should be no problem for you. This was the other one section of notes for this section of the book. So the area of a sector of a circle is theta over 2 pi times pi r squared, which simplifies down to 1/2 the radius squared theta, where theta is in radians. And it says the shaded region of the sector is the circle. It's not shaded in your picture, but it's obviously this section. So what we're doing is we're finding the area of some portion of our circle. So arc length is kind of like finding a part of the perimeter of your circle, whereas the area of a sector is going to be finding the area of that section. This is a good formula to memorize. It's also one that I will probably put on the formula sheet, just because we don't use it as often. There's going to be a lot of formulas that you use over and over and over again, so I'm going to expect you to know them. Some of these that we use like a handful of times will be more likely the ones that end up on the little cheat sheet thing that I provide. So this problem is the center pivot irrigation system provides water to a sector-shaped field with the measures shown in the figure below. Find the area of the field that is being watered. And we're going to round it to meters in this case, or meters square. So instead of finding like how much fencing we would need to put around the outer edge of this field, what we're going to find is how much of it is actually getting watered. And we're going to use our new area of a sector, which is 1/2 radius squared theta. But theta has to be in radians. They don't give us theta in radians, they give it to us in degrees, so that'll be our first thing, is to convert from 15 degrees into radians. Again, leaving it with pi for as long as possible. So now to find the area of the sector, we're just going to plug in all the information we know. It tells us 1/2 the radius squared. Well, the radius in this case is the 321 meters that's listed over there on the side. And that's squared times our theta in terms of radians. So pi over 12. Type all of that in, And hopefully you find 13,500. Oh, dang it. Not only did it go off, and I have to put the whole big long password in again. Back on. Hopefully you get 13,500 meters squared is the area of that sector of the field. So the big thing to remember is that regardless of if we're finding the arc length or we're finding the area of a sector, all of our thetas have to be in radians. And if they're not given to you in radians, you do need to convert over to radians. And the longer you can keep it in terms of pi, the more accurate your answer is going to be in the long run.